So everybody knows where Scott Valley is, but just in case, it's on the other side of the border. And in terms of compliance, we developed this groundwater sustainability plan for Scott Valley in 2021. So it was submitted to Department of Water Resources in January 2022, and then approved in 2023. And what's happening now, it's really what we are working toward. You develop a plan, and then you have to start working on some implementation, because this plan should not stay on the shelf eventually. So what we want to talk to you about today is the recharge project we developed in Scott Valley. And why do we want to do recharge in Scott Valley, and how some recharge can help support the sustainability of the basin and support some of the in-stream flows. So the idea is that everybody here knows there are periods of time where we have high flows in the Scott River, but then this often ends up being a very low flow time in later in the season, when actually there is the need to sustain some of the fish coming up. So the idea is that the entire Scott River is a fully interconnected surface water groundwater system. So if we need to work toward implementation of groundwater sustainability plan, we really need to look into the entire picture. It's not just the groundwater, it's the groundwater and the surface water together. And so the idea came as a sort of as a trial, a pilot project. And we were thinking of just looking at the water budget, the availability of water in the winter months, and how we could eventually store some of that water to be available later on in the season for fish. And the project was kind of an easy implementation, because we are using actually some existing irrigation ditches. So there was no money that was invested for infrastructure. Everything was there. So it was a good pilot to really see how things are happening. And so basically what we are using is really using the Scott Valley Irrigation District system to enhance some recharge during the winter months. And we are trying to monitor now when is this extra water that has been stored in the winter months, when is it making it to the river? So is it really getting into the river at the right time in September, October, when we need to increase a little bit the flows in the Scott River? And this is just how it works out. And the point of diversion is at the bottom of the yellow line. The yellow line is the irrigation ditch, the Scott Valley irrigation ditch, and the water gets diverted there. We have a temporary permit for 180 days. We keep applying for this permit, and the temporary permit comes from the State Water Resources Control Board. We have some requirements, so it's not that we can divert without regulations. So we have some minimum in stream flow that are required at the end of the valley at the USGS 4 Jones gauge to start diverting. But at least we kind of have a system that it's fully in place right now. So the diversion can happen only between January and March, only when the flow at Fort Jones is above. Right now it's a 440 CFS. It has been really complicated to get to the point of having the permit and being able to really make this project happen. And one of the reasons this project is happening is because we really develop a very extensive monitoring plan. So we are monitoring for groundwater levels, for stream flow, and then a lot of water quality and geochemistry. It has been a long journey. We started in 2016, but honestly, 2016, 2022, and 2023, the amount of water that was diverted due to drought, due to whatever kind of condition, was almost nothing. So we basically did about 700 acre feet in 2016, about 800 in 2023. And what we want to present to you today is what happened in 2024, which was actually the first year we really were able to make a little difference. So we were able to divert between January 15 and March 31st, 2,539 acre feet of water. So it's finally is getting to an amount of water that it's that can make a difference. And just to give you a perspective of how we got to this project and how this project relates to everything else that is happening in the valley. When we developed the groundwater sustainability plan, basically we had to decide, the stakeholder, the community had to decide what are the undesirable results in terms of interconnected surface water that the sustainability plan should avoid. And what came out is that condition of depletion of surface water in 2015 were already undesirable. So there was the need to do something better than 2015. So the way we defined the entire success of the plan was we need to reverse the depletion of surface water through different type of projects in the critical months of September through November every year. And the managed aquifer recharge project, like the one that we are presenting today, was simulated through the hydrological model that we have. And we show that this project could have pretty much helped the sustainability of the plan by reversing the depletion by 10%. And obviously we have also numbers that shows how, in terms of acre feet, this 10% works out. But the idea is really 2015 was already something that needed to be improved. And now we can go into the details of the plan.
Okay, so this is a look at 2024 flows. So the 440 CFS is what Laura mentioned earlier. That's the minimum flow threshold at the Fort Jones gauge that we can divert at. So you can see the blue line is the flow measurements at Fort Jones. So you can see for most of the diversion window, which is from January 1st through March 31st, we were way above that 440 CFS. So we were able to divert for most of that window. And then the orange line along the bottom is the amount diverted, which is 10%, up to 10% in Scott River at the point of diversion, and really a fraction of the total flows at Fort Jones. So the data that we're collecting this year, we had 9 groundwater wells that had groundwater level and temperature monitoring, 2 flow stations on Scott River, 1 above the point of diversion and 1 below the point of diversion, and then 5 flow stations along the ditch. So we're really taking a look at ditch infiltration in the different segments to try and quantify some of that recharge that's coming from just the infiltration into the unlined ditch. And I will also mention that these stations are continuous and they're telemetered, so we can track through a website in real time or near real time conditions, and we can adjust as necessary. Okay, so we were able to divert January 15th through March 31st, and as Laura mentioned, a total of 2,539 acre feet. 1,774 were applied to around 10 locations, around 260 acres, and then 765 acre feet were recharged through the ditch. So there is quite a bit of infiltration that's going through that unlined ditch. And the light blue on the right are the fields that were recharged, and then you can see the monitoring overlaid. Okay, so this is a look at the results from October of 2023 all the way through April, so you have some kind of preceding groundwater levels. So it really ranged the response that we saw based on the field location, the duration that we were applying recharge, and the total volume that was applied. So field B, which is the one that has a 17-foot increase in groundwater levels, was where we were applying water the longest. It was almost the entire recharge period. And then the other locations that are 3 and 4 feet had more limited time that we were applying water. So the range in response is 3 to 17 feet, depending on location. And then I'm just going to zoom in on field B a little bit. We do have a transect of wells from the recharge field to the river. And so if you look at the bottom graph, the colors are matching the map on the right. So the well closest to the recharge field, that's the 17-foot increase in purple there. And then the green kind of in the middle and the yellow closer to the river that have very little response that we're seeing, which is actually a good thing for us because we want that delay in the water returning to the river. And then you can also see some precipitation information, 24-hour totals, and then the water diverted for recharge onto field B, the green bars in the middle. And then for water quality, there's some permit terms related to water quality, including no pesticide or fertilizer application after June 1st of the preceding year, and also the requirement to minimize runoff. We did take very limited samples in 2024 following this recharge period, and for 2025 are developing a more comprehensive water quality monitoring and reporting plan that's mostly focused on nitrate and pesticides. So this is a permit term in our diversion permit for 2025. And then I'll pass it to Audra for geochemistry.
All right, good afternoon, everyone. So great to hear about the updates from other folks working in the basin. And I'm going to talk to you a little bit and build upon what Laura and Kelsey shared with you to talk about some natural tracers that we're leveraging to try to get a little bit of a clearer picture what's happening on the Scott River main stem near this Scott Valley Irrigation District recharge area. And so we're going to be talking about two different tracers that we utilized in 2024. And some of the things that we're hoping to glean insights on from these tracers are periods of interconnectivity. When do we see apparent increases in groundwater influx to the river? And then also perhaps shifts in water source contribution. So this is, again, just one of the puzzle pieces that's going to fit together with the physical monitoring, the modeling that's happening. And because this is the first year that we went through and did this time series monitoring, we still have a lot of work to do to integrate all these pieces together. But I'm going to show you some preliminary results that can give you a sense of what we observed. All right, and again, I kind of mentioned this idea of time series. In dynamic systems like this, doing this type of time series sampling is really informative and shows us what's happening through time and perhaps periods that are more important to the salmonid life cycle. We're kind of seeing what's happening going on in the river. Okay, let's go ahead. All right, so I'm going to first talk about radon. Now, you probably don't think about radon a whole lot. Maybe you've heard about it in people's basements, perhaps causing health issues. This is a radioactive noble gas that's ultimately produced from uranium. Uranium shows up in almost all geologic materials in some small amount at least. And so radon is pretty much ubiquitous, which is a good thing for us. So what we can do is, because it's a noble gas, it doesn't interact chemically with anything in the subsurface, but it does accumulate. It has a short half-life of only 3.8 days, so it doesn't accumulate too much and stick around over long time periods. So it's going to be something that kind of grows into what we call equilibrium quickly and accumulate in the groundwater, in the subsurface aquifer, and once it gets discharged to a surface water, it's going to dissipate really quickly through degassing. The result of this is it's a really nice localized tracer for groundwater influx to surface water systems. And so what you can see here is a little map of one of our study areas on a tributary to the Scott River. And this just gives a sense for some of the spatial variability you can see over pretty darn small length scales. So this is only hundreds of meters away. We see a lot of variability in the radon that's apparent in the surface waters. And again, this is going to be some weird units, picocuries. That means radon is decaying about 2 times per minute. It's a proxy for radon concentration in the water. So that's how we're going to think about it when we look at the graphs. All right. And again, when we're thinking about gaining conditions in a qualitative sense, we expect relatively higher radon activities or concentrations. In non-gaining or losing situations, we expect to have lower radon. So let's see how the time series looked near this infiltration, this managed aquifer recharge that Kelsey talked about. So you can see on the map here, we have 4 sites that we sampled for time series that were adjacent to some of the recharge area that Kelsey talked about. Recharge is happening on the east side of the river. You see, again, flow direction is from south to north in this situation. And we have, oh, unfortunately, my axis, it looks okay here. We have an axis that goes up to about 60 picocuries. Groundwater might be 200-ish, 250-ish in this area. We're still getting a better handle on that. But again, higher radon concentration or activity, we're thinking higher from a qualitative sense, higher contribution of groundwater to the discharge we see at that moment in time. So you can see that there is, if we just look overall, an increasing seasonal trend as we look from April through the end of September in 2024. There's a local maximum or in July, which we find interesting. That's something that we're going to dig into more and see, is this related to some precip? Is this related to localized pumping that's occurring? But again, overall, we are seeing an increase in the radon activity, which is consistent with stronger gaining conditions as we go later into the season. All right, so the other thing that we did to look at the connectivity at the site that was farthest downstream, Eller Lane, downriver, I should say, is we used a push point sampler, which is just a stainless steel hollow tube that you can push into sediments. Has a very selective zone from which you pull water sample. And we took a profile from the stream bank on the Scott River. Now, if we have kind of a classic gaining condition illustrated by this cartoon, we would expect to see increasing radon activity with depth, as we have a higher proportion of groundwater flowing into this stream bed. And so again, what we do see illustrated here is we get up to about 200 picocuries per liter. Again, what we expect to be approaching kind of a background concentration for groundwater in this area. And we have also in the sample water above a lower activity, but this is really nice evidence for a connected stream condition late in the season. The sample is collected at the end of September. So again, some nice evidence to help us understand what's happening along this section of the river. All right, so not only did we do radon, we did stable isotopes of water. That might be more familiar to some of the folks who work on different hydrological studies and water quality. But just to give us a sense, so we're looking at the relative proportion of heavy to light isotopes in this delta notation for water. So for hydrogen and oxygen that make up these water molecules. So this is a very intrinsic tracer. It's the water itself as it moves through. So different factors are going to impact the isotopic composition of different water masses. An individual storm could look different. Winter versus summer precipitation can look different. So this is a really nice way to fingerprint different water masses. And we usually look at these data results on a dual isotope plot, which is kind of what I've mocked up here. So you can see mixing, linear mixing between different water sources. You can sometimes see impacts from things like evaporation that produce kind of unique signals in the water isotopes. And the idea here is that if you can characterize the system and look through time, the hope is that you can start to see different water masses, maybe mixing transitions from contribution of one source to another through time. So let's go ahead and take a look. Here's our dual isotope plot. Things are negative. Again, that's because this is a standardized ratio of heavy to light isotopes. And so things are negative in this space. So we do again see as we move from March on through, we had some delays in data. This goes to the end of August. We see kind of this step towards a distinct isotopic signature. Again, consistent with a transition in water source contribution through time. This could be a shift perhaps in flow regime from more snowmelt domination earlier in the season to maybe a little bit more base flow support later in the season. So again, we can kind of put these together and get some picture of what's happening. All right, so I am running a little short on time, so I will keep cruising along here. I want to give a quick look at some work that we did along Kidder Creek, which is a tributary to the Scott River. It's another place where we have an unlined earthen irrigation ditch that early model results sort of indicate is actually leaking water back into the aquifer. And that water, we think, is getting recaptured by the river, or sorry, the creek, which again is another important location for salmonid habitat. And so this is not a huge study area, but we went ahead and at these different locations collected, again, radon and water isotopes to see what the seasonal trends look like. So again, here we're looking at radon, higher activity, higher concentration, more suggestive of groundwater contribution at that location. So again, you see that we have this diversion point where water is being sent into the unlined irrigation ditch. I'd like to focus you on that brown diamond. That doesn't really change. That's a nice proof of concept. We don't expect the irrigation ditch to be a gaining condition at any time. It stays low throughout the entire sample period. That's nice. It stays close to the detection limit. It's not acquiring any radon. And we think, probably a losing portion of the ditch. If we look at Kidder Creek at the diversion, the pink here, we can see that we have modest increase through the season, and then we have much stronger gaining conditions at this Kidder Creek downstream of the diversion. And so again, we're going to look a little bit at some more limited sampling we did at this, what we call among our group, the salmon pool. So it's a deeper pool where we have seen some fish, and there's an undercut bank here. And this is a place where we had very limited sampling, but we did see an increase through September. And when we went ahead and collected some of the seepage using our push point sampler, we saw that this was very high in radon. So this looks like it might actually be groundwater transiting over laterally and joining up with the creek. So this is something we really are looking forward to exploring more next year. All right, so how do water isotopes look at this area? So again, we're just gonna, because we don't have a ton of time, we're gonna look at these kind of overall step trends as we move through the season. Here we have more limited data for May through August. But again, you see a shift from what we call lighter, more negative isotope composition through time into heavier or more positive. And so again, this is consistent with a shift in water source contribution through the season. So what do these kind of tell us together? At both sites, there does appear to be a seasonal increase in the relative groundwater contribution to the sites and a shift in the water source contribution. We are hoping, this is kind of qualitative right now, we're hoping to transition into getting more quantitative measurements of the amount of groundwater we can account for at these different sites. We're also hoping to combine this with some other temperature measurements and other finer scale physical measurements as well. And so we think this is an interesting and maybe unique way to support the other types of efforts that are happening, the physical measurements and modeling, with some sort of like on the ground direct observations. All right, so thank you so much. I'll pass it back to Kelsey to wrap it up. Or Laura.
Yeah, so this is gonna be very brief. We are kind of finding some interest and also a lot of stakeholder interest in this type of project. So the 2024 success year in terms of application helped us really design a better monitoring plan. We hope to be able to do it again next year. And the goal is to have a multiple years of implementation to really see what happens and to keep collecting this information. So we already applied for a new diversion permit. So hopefully it all depends on the winter. If we get a good winter and we get enough flow, we will be able to keep working on understanding what's possible depending on the water year types, what are the potential long-term benefits of this type of project, and also if we think about strategies for maximizing this recharge benefit. Thank you.
Do we have any questions?
Here you go. I don't know, maybe during the winter, it's not a consideration, but is there any evaporative loss that you're accounting for? Sorry. You do.
Yeah.
Zoom folks.
No problem. No, no, because it's all between January and March. So that's not something that it looks like we don't have to really consider any significant loss from evaporation.
Thanks. Lots of interesting stuff. I was wondering if you could just clarify what your plans are for, writing a report or publication on this, and then also in for future years in the long-term monitoring, would you collect this sort of the same data even if there wasn't a recharge project, just to sort of be able to compare with that, or how do you see that? Or do some pieces stay in and some pieces go out if there's not enough water to do the project?
Yeah, so in terms of reporting, we have to report every year to the State Water Board, and we kind of thought that these reports were fully available. Actually, you need to request them. So if you request to the State Water Board, the Scott Valley Irrigation Niche diversion report, you'll get it. Unfortunately, it's not really that you go there and you get it. So I'm sorry. You can also request it to us. I think we can share it. It should be public. It's just not available on a website. In terms of data collection, so we really have these groundwater sustainability agencies as this funding through March, April 2026. Our goal would be to do as much as we can in this 2 years window. So and now it's a year and a half actually. So we will keep doing it, and really because we want to understand what are the conditions with the recharge, without the recharge, so we can eventually kind of nail down which are the biggest components in this water cycle. So we'll try to keep. We will try. Our goal is to repeat this experiment, and so have the same results for next year and be able to see what this tell us.
I am curious if there are any concerns with diminishing the peak winter flows. I think we heard earlier today about the importance of high flow events to transport sediment and keep the annelids at bay. I'm just curious about the consequences of diminishing high flows during the winter.
Yeah, and this is why we put this graphic there, because this really tells you a little bit of the story. So the blue is the flow at Fort Jones throughout January through March. And so the flow was always way above 500. And what we were diverting was eventually between 10 and 20 CFS. So it's really such as basically what we were diverting is the orange line down there. So you are really not diminishing the peaks because of requirements through State Water Board and CDFW. We do biological monitoring every day. So there is somebody that goes out every day. There is a diversion that goes 100 feet above, 100 feet down, downstream of the diversion to check that nothing is impacted in terms of fish or anything. But this year really because of this flow, and we are talking about 600 700 CFS and we are diverting maybe 15, it was kind of in the range of the error of the measurements probably, so you couldn't see any impact on the peaks.
Any other questions?
All right, from Zoom, do you have any control fields to sort out natural groundwater increase over the winter versus the 2 fields showing a minimal increase?
Sorry, what did?
Actually, maybe I will have that too.
Sorry.
Did you have any control fields to sort out the natural groundwater increase over the winter versus the 2 fields showing a minimal increase?
So the nine observation that we mentioned in the map, they are just part of a much bigger network of data collection. So we are trying to monitor a little bit everywhere and see what's the response in the fields where there is recharge versus the fields where there is no recharge. So okay. Okay. Oh, and we added also some other on the other side of the river, so we can see what's the contribution due to the recharge.
So does this get us closer to answering the question of how much water do we need to divert in the wintertime and apply to the landscape like this in order to see 40 CFS in the Scott River in August? Like, I mean, like your previous iterations of this, where you're able to kind of demonstrate a very modest improvement of flow, but nothing remotely in the ballpark of what's needed. So are we getting closer to understanding that?
That's the idea, Craig. And I feel like that's why we hope to be able to do it for a second year, so we can have a comparison. Also because this past winter has been kind of unique. We really had flow for 3 months in a row, and in the previous winters it was not possible. So the idea is we really want to be able to, with some uncertainty, but really quantify how much water is making it downstream into the river in September, October, when we really want it. So, and the next step, what we are doing now is simulating all these scenarios through the hydrological model that we have, and then use the model for running future scenarios.
Nobody else has a question, I'll ask another. What is limiting the capacity of the amount of water that you could recharge in the past year? Was it the ditch? Was it the number of fields you had access to? Because isn't the ditch capacity higher than 10 or 20?
Yeah, so it took a while to really understand how much the ditch could really take without being dangerous for people living there. Because in the first experiment, there were some basement that flooded just because there was too much water in the ditch and it was flowing out. So the biggest limiting factor is anyway this 440 at 4 Jones, and there are some requirements also at young stem. So the point of diversion, we can divert only 10% of the natural flow at the point of diversion. So if the point of diversion is 300, it cannot be more than 30. So there are all these requirements that are in the diversion permit. And so we need to meet 4 Jones, we need to young stem, and then we need to check what's happening in the ditch. Actually, right now we have even more stakeholders interested in having water applied. So in principle, we have the capacity to take more. We just need to figure out how to make it happen.
Because I would think that like during the early part of irrigation season, the ditch would be running at sort of its max capacity, right? So are people's basements not flooding then? They're only flooding during the winter when because it's raining or something?
It's mostly, in any case, the ditch at most is 40. So still, and they prefer, if they know that there is a precipitation event coming in the wintertime, they don't really want to have the ditch running at 40, because then if the precipitation comes, the problem is that in the summer or early in the irrigation season, maybe you don't expect the big precipitation events that can happen in January or February. So you always need to have that wiggle room to be sure that you can make it work. Betsy? Oh, sorry.
Yeah, so the maximum in our permit we can divert is 30 CFS at SVID, point of diversion. And so the maximum that can be applied in 1 year is 5,400 acre feet. I think this year, because you saw the permit history and the amounts of water applied, this year we had a really slow ramp up and lots of communication with landowners to kind of listen and hear what was going on and make sure we weren't going up too fast. So I think this was a good year to work out the logistics and then also get some data. So I think in future years, we'll have a better kind of strategy and schedule for that. But that's a good question.
Yeah.
Keying off Eli's question, historically, the practice was to run ditches all winter. So the historic stream flow at the Fort Jones gauge would reflect the inputs related to that historical practice. Then we had the curtailment and the cutting off of inefficient irrigation through earthen ditches. And so have you done anything to tease out? I mean, if the 10% is above, you know, how are you comparing historical conditions to the drought to the now application of water in terms of potential stream flow?
So we made a comparison with, so 2022 is when the ditches were dry because of curtailments. And what we could see is that when the curtailments was lifted and the water started going into the irrigation ditch, it took basically 10 days for the water in the ditch to travel 1 mile. So when the ditch is very, very dry, because they are aligned ditches, it's just losing so much water on the way. And it really took, basically that's the reason why we were not able to do any recharge, because it took so long to just make the ditch wet. So we compared the 2022, 2023, and 2024. For before, we really don't have data. I mean, we don't know exactly what was going into the ditch, what is the losses from the ditch itself. So we are trying to reconstruct let's say the history, but it's not that we have the data. Also, the groundwater data were not there before. Now we have all this information. So we are trying to do our best to try and to understand how the system has evolved, actually.
Thank you.
Thank you.